Welcome back to Introduction to Software Reverse Engineering. In this module, we will examine variadic functions, their use, and the ways to find and identify them, as well as their arguments with Ghidra. Let's dive in. Welcome to Module 8. In this module, we will look into functions that can handle various numbers of arguments gracefully, thus adapting to the input and engineer's needs dynamically, the variadic functions. We will examine the theory behind their implementation and look at the examples of built-in and custom implementations of such functions. Remember that all the materials covered in this course are available on GitHub. These materials include the source code as well as compiled binaries that are exactly the same binaries as reverse engineered and shown in the videos throughout this course. Meet the shapeshifters of the coding world, variadic functions. These functions can take any number of arguments, making them super flexible and powerful. But with great power comes great responsibility and some potential security risks. Let's break it down. They can accept any number of arguments, even none at all. They can handle different data types like strings and integers. They often rely on format strings or parameter counts to figure out what's going on. Some famous examples include printf and scanf functions, which are staples of C programming. But beware, if not implemented carefully, variadic functions can introduce security vulnerabilities like format strings attacks. When working with functions, you'll probably encounter two types, those that demand a precise number of arguments and those that are more flexible. This distinction comes down to arity, a fancy term for the number of arguments a function takes. There are two main types of arity. Fixed arity, functions with a set number of arguments. Think of a function that takes two numbers and returns their sum. It's straightforward and predictable. Variable arity, functions that can handle any number of arguments. These are often implemented using variadic functions, which use a special parameter represented by ellipses to accept a variable number of arguments. In variadic functions, the variable arguments are always at the end, and a special parameter often helps identify how many arguments are being passed. This flexibility can be powerful, but it requires careful handling to avoid errors. So how do variadic functions actually work in C? Calling convention. Variadic functions in C always use the C declaration, which means that the caller is responsible for cleaning up the stack after the function execution. This makes sense since the function itself does not know how many arguments were passed. Counting variable arguments. To access the variable arguments, the function needs to know how many were passed in. This is typically achieved by passing the number of arguments or a string template, like in function printf. Accessing variadic arguments. To iterate over the arguments, C provides a set of macros, va start, va arg, and va end. These macros help you access and process the variable arguments. Before going any further, fire up Ghidra and import two new example programs. Built-in functions and custom functions example programs are available on the GitHub repository. Now, let's take a look at the source code of built-in functions.exe example program. In this video, we will reverse engineer the following function. The function contains three function calls, two functions listed just above the function in question, and a call to printf function with arguments of various types. The function in question after the compilation is shown on the screen. First of all, note that Ghidra properly identified all three function calls. However, most of the arguments are missing. It is always a good idea to click through the decompiled code in the decompile window and see whether the assembly listing matches the decompiled version or not. The second function call is missing the second argument. However, it is present in the listing window. Right-click on the function on line 6 and select Edit Function Signature context menu option. The Edit Function window will appear on the screen as shown right now. Change the data type of the first parameter to character pointer and add a second character pointer parameter so that the function signature matches the definition as shown on the screen right now. Click OK to apply the changes. Once the changes were applied, function call changed and Ghidra now shows the second argument of a function call as well. Now, let's take a look at the function call on line 7. Ghidra shows only one argument. However, the listing window shows a lot of push assembly instructions, strongly suggesting that there are more arguments to the function call. Moreover, function arguments that contain printf-like formatting values should always fire up your interest in terms of checking for missing function arguments. Right-click on the function on line 7 and select Edit Function Signature context menu element. The Edit Function window will appear on the screen. Check the var_args checkbox in the Edit Function window to instruct Ghidra that the function is a variadic function. Then, change the type of the first parameter to a character pointer and click OK to apply the changes. The decompile window will update to reflect the variadic nature of the function call and pull in previously hidden function arguments. However, the data types of the arguments are displayed as if they are either string or integer value. Double-click on the first argument of the function on line 7 to see its body in the listing window. The format string contains placeholders for a string, 2 integer numbers, a single precision floating point value, and a double precision floating point value. Right-click on the function on line 7 and select Override Signature in the context menu. Override Signature window will appear on the screen. This window displays the currently identified function signature with all the parameters. Note that most of them are undefined for. Given we know the format string, we can safely change the data types for the function parameters using this window. Change the function signature so that the data types match the format string placeholders as shown on the screen. Then, click OK to apply the change. Once the function override was applied, the decompile window properly displays the values passed into the function as its arguments. Now, let's inspect the body of the function itself to see if it has a proof or a clue hinting that it is indeed a variadic function. The body of the function indeed contains a strong hint that the function is a variadic function. See the use of stack of set automatic variable on line 9. Such stack of set automatic variable as used in Ghidra usually means that either a parameter or parameters are missing in a fixed arity function, or the function is a variadic one. Now, let's inspect the body of the function at line 9. This function is a long one. I'll leave it to you to familiarize yourself with it on your own time. An interesting part to it is that it contains a lot of checks for specific characters, such as shown on the screen. These special characters checks are the checks for formatting templates in the format string. These checks should tell you that this is either a printf or a scanf function, or a function in the same family of functions. Now, let's go back to the original function we were reverse engineering. Rename the function on line 7 to printf. At this point, you should already know how to do so. Variadic functions is a generally available feature of the language. It is not limited to special and limited number of built-in out-of-the-box functions. Creating and using custom variadic functions allow you: first, write more usable code. One function implementation can handle multiple use cases, reducing code duplication and making maintenance a breeze. Second, simplify complex logic. Variadic functions can streamline your code, making it easier to read and understand. And lastly, convey intent more clearly. By allowing functions to handle variable inputs, you can make their purpose more explicit and intuitive. Let's take a look at a custom variadic function implementation and its reverse engineering. I implemented a very simple variadic function that formats the input format templated string with the values. This function uses va_start and va_end macros. It is also using va_printf function that is designed to format the string using va_list argument instead of variable list of arguments. The main function of custom functions.exe program after the compilation is shown on the screen. Again, note that Ghidra did not identify all the parameters correctly. For example, a function call on line 7 shows an unknown data member as the function parameter. However, if you double-click on it, you will see a small format-like string in the listen window. Generally, Ghidra has a hard time identifying short strings automatically. To change the data type of this short string, right-click on it and select Data String in the context menu. After the string data type was applied, the string is properly displayed in the listing and the decompile windows. However, the rest of the parameters are still missing, as shown by the examination of the assembly instructions. Now, let's inspect the same function call on line 9. See how many arguments Ghidra is not showing in the decompile window. Let's inspect the body of the custom variadic function. See that there is that automatic stack variable as we discovered earlier, strongly indicating that this is a variadic function. Also note that after the compilation and decompilation, there is no va_start and va_end type conversions for the function parameters. Right-click on the function name and select Edit Function Signature in the context menu. The Edit Function window will appear on the screen. Click the varargs checkbox, change the first parameter data type to character pointer, and click OK to apply the change. This will instruct Ghidra to interpret the function as a variadic function that always has at least one parameter with a format string. After the changes were applied, Ghidra added ellipses as the function parameter. Now, back to the main function. After all the changes we have done, Ghidra was able to pull in all the missing values for the function calls in the decompile window. Variadic functions can be powerful tools, but they also come with a warning label: use with caution. If not implemented carefully, these functions can introduce serious security vulnerabilities, including bugs, crashes, and exploits. One classic example is format string vulnerabilities, which occur when user-controlled input is used as the format string in a variadic function like printf. This can lead to disastrous consequences, including information disclosure. Sensitive data or stack memory can be leaked, compromising confidentiality. Code execution. Attackers can execute arbitrary code by overwriting function parameters or return addresses, taking control of your system. Denial of service. The program can crash or behave unexpectedly, causing downtime and disruptions. The takeaways. Variadic functions require attention to detail and careful handling to avoid these security pitfalls. We have seen how variadic functions can introduce security vulnerabilities, but what can be done to prevent these issues? Let's explore some of the mitigation strategies. Use constant format strings. Avoid using user-controlled input as format strings to prevent exploitation. Validate user input. Ensure user input conforms to expected formats and ranges to prevent unexpected behavior. Use safer functions. Consider using sn_printf instead of printf to reduce the risk of buffer overflows. Other security considerations. Argument type mismatches. Ensure argument types match the format string specifiers to prevent unexpected behavior. Buffer overflows. Be mindful of buffer sizes when using variadic functions like sprintf. We have looked at the variadic functions and their implementation in the context of reverse engineering, but our journey doesn't end here. In the next module, we will explore the world of static and dynamic linking of C runtime library into executables. And don't forget, all the course materials are available on GitHub. Stay tuned for the next module, where we'll take your reverse engineering skills to the next level. If you are looking to dive deeper into software reverse engineering, I'd like to recommend my book, Software Reverse Engineering: Navigating x86 Windows Applications with Ghidra. This course draws heavily from the book's content. However, the book itself contains many more examples and insights that can help developing your reverse engineering skills. The book is available in both print and digital Kindle versions on Amazon, making it easy to access and read wherever you are. Additionally, the book covers subjects not discussed in this course, such as reverse engineering of C++ programs, classes, virtual functions, and more. I encourage you to check it out. Thank you so much for watching and learning with me today. If you found this video helpful, please hit that like button and subscribe for more content like this. Your support means a lot to me. If you have any questions or topic you'd like to discuss, leave a comment below or shoot me an email. I'm happy to chat. If you'd like to support me and the channel financially, you can do so through Ko-fi or Patreon. Links are in the description below. Thanks again for watching, and I will see you in the next video.